So we've been looking at Cartesian geometry. Now we're looking at Euclidean geometry. Now, the thing is, the ideas are interchangeable. So, as you saw in Cartesian geometry, we used often some Euclidean geometry ideas to solve problems. Happens less in the reverse, I suppose, but there's no reason why you couldn't use coordinate geometry ideas to solve Euclidean geometry problems if you wanted to. Some definitions to start off with, though. So when we're setting out our solutions, our proofs, some terms, so notations we can use instead of writing all the words out. And obviously we know the two vertical lines are parallel and the upside down T, perpendicular, 3 horizontal lines, congruent, 3 vertical lines, similar. The triangle, therefore, the upside down triangle, probably less often used, but that just means because. So some people use it in their reasoning. They'll say, oh, because of this. Terminology that we use in geometry. So produced. Produced means the line is extended. And the way we use the word tells us how we extend the line. So if here's an interval, I suppose, would be more correct than line. But there's xy. If I was to say xy is produced to A, so the naming of the interval tells us the direction we're going. So we're going x, y, produce to A. Okay? And so if I wanted to go the other way, I would then say yx is produced to B. Because remember, when you're writing your proofs down, what you're writing down is an argument that someone could reproduce and recreate your solution. And so they need to know exactly what you're doing. So if you're saying I'm going to produce it, they need to know which direction did we go and so on. Foot. Foot means the base or the bottom, but it's not necessarily at the base or the bottom of the picture, of course. The most common use of it, I guess, is foot of the perpendicular, which basically means where the two lines meet in the perpendicular, and we call B the foot. So B is the foot of our perpendicular. Collinear, well, we talked about that in coordinate geometry. So the points lie on the same line, collinear, and concurrent is like the reverse. The lines go through the same point, so they share a common point. Transversal, most often seen when we're talking about parallel lines, but it's not restricted to parallel lines. A transversal is simply a line that cuts 2 or more other lines. That's a transversal. Some conventions when we're naming shapes, and angles for that matter, we always name them in cyclic order. Because again, if someone wants to reproduce your diagram, they need to know the order of the vertices. So we understand, okay, it's in cyclic order. So this particular angle, I could call angle ABC. And now the angle symbol, some people start with the angle symbol at the front. The other way of doing it is putting the little, what do they call that, the caret?
Shuffle.
Thank you. But we put it above the vertex of the angle. So it's another way of naming it. If there's no ambiguity, then it's okay just to call it angle B, because there's no confusion. If you had, say, vertically opposite angles, you wouldn't call it angle B because there's 4 possible angles you might be talking about. So if there's no ambiguity, I think it's just safer just to always call it with the 3 letters, then there's never going to be a problem. So there's my quadrilateral. Lots of different names I could call this because it's cyclic. It doesn't matter whether you go clockwise, doesn't matter whether you go anti-clockwise. So it could be, VP QT, QP VT, QT VP, and so on and so on and so on, as long as you're going around in the right order. Parallel lines, when we talk about parallel lines, name them in the corresponding order. So a situation like this one, I would say AB is parallel to CD, not AB is parallel to DC. Right? So name them in the same order that the lines are going. Equal lines, as we know, we mark them with the same symbol, quite often just a dash or a couple of dashes. So there's a quadrilateral, which I've marked in, and we're saying all opposite sides are equal, basically, with our notation here, thus making this shape. Could be a rectangle, but we don't know that for sure. Yeah, parallelogram would be the best we would know for that one. Okay. Now, when we are constructing our proofs, this is probably the vital part of this topic, okay? Because a lot of times it's not the final answer we're really interested in, it's your thought process or how you're arguing your position, if you like. So when you are constructing a proof, if you're going to write a line down, you can't just write any garbage down. Okay? You can't just make things up. A line you write down, first of all, it might be given information. They often give you information in the problem. So we know that to be true. We can write it down. Okay? So, mind you, don't assume that they've given you information they haven't. And here's a classic one. Sometimes you're told two sides of a triangle are equal. And so people will say, oh, well, therefore these angles are equal because their base angle is an isosceles triangle. Well, hang on. You haven't been told it's an isosceles triangle. All you've been told is two sides of the triangle are equal. Technically, you need to prove it's isosceles before you can use the feature of an isosceles. Okay? If you're going to construct a new line, well, then you write in clearly what your construction is. So again, if someone was to try and reproduce your proof, then they know exactly how you've constructed and what you've done. It's always a good idea, certainly with the more complicated geometry problems, to include the diagram as part of your solution. So that way, if you do introduce new letters and you haven't written in there, at least they can refer to your diagram and they'll know, oh, okay, that's X or that's Y. A recognised theorem or assumption. Okay. And by recognised comes from our wonderful list of different theorems that we end up looking at. Now, you see I've written here, the theorem should be explicitly stated. Right? Whether that be in the algebraic statement or whether it be in the reason. I've done it in both here. So say I was using the angle sum of a triangle theorem. I would say, oh well, these three angles add up to 180. Because that's what the theorem is. The angle sum of a triangle is 180. I've also said in my reasoning, angle sum of a triangle is 180. I probably in my reasoning didn't need equals 180 because I've said that explicitly in my algebra over here. I could have just said angle sum of a triangle. A lot of people, for their first line, would write down for this sort of problem, angle A equals 180 minus 25 minus 120. Well, that's not what the theorem is. Whatever your reasoning is, though, you need to be clear but concise. It's not an essay. We don't want to be reading pages and pages of explanations. Okay. And, of course, the final thing you might write down is something that logically follows from other lines you've already written down. So you say, oh, well, because of this line and because of this line, I can conclude this. Okay. And that's pretty much it. All right, let's recap the different angle theorems. Probably started off with this one. Right? That angles in a straight line add up to 180. And if I'm using that theorem, let's say here's my little problem here, x and 30, and they want me to do it with reasoning, then I would write down x plus 30 is 180. Yeah, sure, I can look at that straight away and say x is 150. But if they want it with reasons, I'm writing the theorem down. I'm saying these two angles add together to give 180. How do I know that? Well, the reason I use is the fact that it's a straight angle. And we know straight angles are 180 degrees. Be careful. Some people for this would write down supplementary adjacent angles or something like that. You can only use that if there's two angles. If there was three angles on a straight line, you could not say supplementary adjacent angles. Because what is the definition of supplementary angles? Two angles that add up to 180. So if you had three angles, you couldn't use that reason. And that's why I guess I just always use straight angle. It doesn't matter how many angles I've got there. I can say, well, the sum of them is going to be 180 because it creates a straight angle. And my solution, of course, 150. The next one we usually see is good old vertically opposite angles. And of course, vertically opposite angles are equal. So for this particular problem, I simply, oh, well, 3x equals 39. Vertically opposite angles are equal, not vert op. Right? Vert is French for green. Op might mean, could mean opposition, could mean all sorts of things. Okay? Remember, what I said was with abbreviations is acceptable geometrical abbreviations. The angle symbol is a geometrical abbreviation. The equal sign is a geometrical abbreviation. Vertically does not have the abbreviation vert. Where do you start? Where do you finish? Some people might go VO. I mean, at what point do we say yes? What point do we say no? So X is 13. No, I guess you could leave out the word R there because vertically opposite angles equal would probably be okay. All right, then we go to angles about a point. But remember I'm saying reasonings should be concise. So rather than saying angles about a point, well, what type of angle is created when we have angles about a point? A revolution angle. So I would say that all these angles add together to give 360 because they are creating a revolution angle, or a revolution equals 360. And so that's 75. All right, whilst we're talking about angle theorems, then we moved on to parallel lines and all the different angles that are involved there. Remember, the names are telling you the types of angles. Alternate, or to say it another way, alternate. Okay? Because that's what the angles do. They alternate on either side of the transversal. Okay? So in our diagram there, C and F, they alternate on either side of the transversal. Okay? The other pair, of course, is D and E. With alternate angles, remember they must be inside the parallel lines. The ones outside can't be alternate angles. We'd have to do a combination of things there, maybe vertically opposite, then alternate, or something like that. All right? Remember, must put in parallel lines because there's actually two conditions for them to be equal. Right? One, that yes, they are in the alternate position, but the second condition, that the lines are parallel. You can have alternate angles on lines that are not parallel. It's just that they're not equal. So you need to mention that. I've just written parallel lines. If the lines were named, then I'd probably put, well, AB parallel to CD or whatever the name was. Corresponding, when we talk about geometry, means in the same position. That's why you have corresponding angles in congruent triangles, although these days they get you to say matching angles, but you might have seen it, corresponding angles in congruent triangles. They're in the same position. Corresponding angles on our parallel lines are in the same position. So A is in the same position as E on the other parallel line. So they're corresponding. B and F are in the same position. C and G are in the same position. D and H are in the same position. So they're all corresponding angles, and they are equal as well. Co-interior. Co, together, interior, inside. So that, again, we're on the inside of the parallel lines, but this time, instead of alternating, they're together. So the co-interior. And they add up to 180. So C plus E is 180, and the other co-interior angles we have there is D plus F is 180. So let's do a classic little parallel line problem. We need to find X, we need to find Y. Well, X is, of course, the easiest one to find, so I'll do that one first. X plus 65 is going to be 180, straight angle. And again, when it's named, I'll name the angle. So I'm talking about the angle CQD. It's good to name it. We want to avoid ambiguity. If I didn't name it, although you have to be pretty silly to go for the other line, but technically there's lots of different straight lines there. So I'm naming which one I'm talking about. So X is 115. Now I've got to try and work out Y, but in order to do that, I'm going to need a construction. Now there's different constructions I could do, but the one I've chosen to do is to construct a new parallel line. So I'm going to construct XY. It's going to be parallel to CD, and it's going to pass through P. So there it is there. Okay. So now I'm going to find the angle XPQ. It'll be 65, alternate angles. And I'm talking about the lines X, Y, and CQ here. Again, now it's good to name them because I've got three parallel lines. Then I can also say, well, XPB plus 120 is 180. I've got co-interior angles there. And so that's 60. But together, BPQ and XPQ plus XPB, we're talking about the same angle. It's just a different way of writing the angle. On the left-hand side, I've written it all as one angle. On the right-hand side, I've written it as the sum of two angles, but it is the same angle. And so we just say, well, that common angle. We're talking about the same angle here. And so they add together to give 125. All righty.